Good morning. We'll push forward. So I want to talk about Schrodinger equation, still Schrodinger equation, but in 3D. So, like, this is the nice thing about this. We said this is the equation we need to solve in most general form. Now I am like going back to like wave formalism. If I need to, I can also go to like abstract bracket notation, but here we are going to do a little bit wave mechanics with a little bit more calculations. So this is valid in any dimension, but in 3D, what we have is like this psi will go to a function of x, y, and z, and there is possibly t. And also h is going to go to a vector p squared over 2m plus v as a function of another vector. If you want, I can write it like this: x, y, and z. And this p squared is px squared plus py squared plus pz squared. And each p, let me write it like pi, is exactly the same, r minus I h bar, gradient in that direction. And this is actually good. Let me appeal to vector form. So this is like a vector, and this is gradient. Like commutations, you can check. This is like a 30-second calculation. Any xi, take any momentum. If they are like the same direction, like x px or y py or z pz, they commute as before. The commutation relation is as before. If I and j are different, they just commute. They are independent. And this p squared over 2m, p squared over 2m in 3D is going to be minus h bar squared over 2m Laplacian. For example, in Cartesian coordinates, this is going to be del squared del x squared del squared del y squared plus del squared del z squared. Right? Like normalization is also the same with more integrals. So we have, rather than dx, we have d cube r over all volume. This psi squared is equal to 1. And so this is time-dependent Schrodinger equation. If the potential is time-independent, which is going to be the case 99.9% of the time for us. If that's the case, we can try separable solutions. Separability is the same. So it's like we define this psi and x, y, z, and t is equal to some only x, y, z part, some xn, x, y, z part, and there's some exponential part. And this part is going to be found from time-independent Schrodinger equation, which is, let me also write it, minus h bar squared over 2m. Now del squared is psi n x, y, z plus v of x, y, z psi, also x, y, z, n is equal to En, the same thing. Good. So as like maybe I can give you a couple of exercises and jump into the tedious part immediately. So like exercise. There's like a trivial exercise that everybody should do if you have never done it before. Like take 3D infinite box. What this means is like v of x, y, z is equal to 0 if x, y, z is inside some domain from 0 to a and infinity otherwise. Right? Take this and find eigenvalues and eigenfunctions. And identify degeneracies of ground state and excited state. And where? Take 3D infinite box. This is v of x, y, z is equal to 0 if x, y, z is inside 0 to a. Like there is like a three-dimensional box. In each direction, if you are inside the box, potential is 0. If you are outside, it's infinity. So this is almost trivial example, so let me not spend time with that. And second exercise, consider, right, simplest thing is free particle, but it's, you know, it's actually a little bit more complicated than a box. Consider free particle, but in 3D. And for example, by solving the time-independent Schrodinger equation, find this psi of k of r 1 over 2 pi cube e to the I k dot r. Right, you need to solve each component separately. And if you also incorporate time dependence, you can also do that. T, this is going to be minus I omega k times t, and I think do I have, yes, I think it's like this, and h bar omega k is going to be h bar squared k squared over 2m. This is also almost trivial, and also normalization is going to be psi of k, psi of k prime is going to be delta of k minus k prime, and the vector delta means, so this thing, let me write it like in more general case, delta r minus r prime means delta x minus x prime, delta y minus y prime, and delta z minus z prime. This is the meaning of vector delta function. Good?
Did you write r plus r inside of that?
R minus, this is minus. Let me make it clear, so this is minus. Okay, now let's come to the tricky part. Let's consider central potential. Which will work for some time. So if v of x, y, z is not a function of x, y, z separately, but a function of only r, and r, you can see I try not to put a vector sign. R means x squared plus y squared plus z squared. That's the distance to the origin. We call this central potential. And in this potential, it is favorable to use spherical coordinates, because in that case you can separate the variables. So let's consider the spherical coordinates. So this is my Cartesian coordinate. So I have like some vector. So this vector has like some perpendiculars. So this is perpendicular. So this is r. So this angle is, I'll call it theta, and this angle I'll call phi, and this thing is x, y, and z. I think engineers use it the other way, so be careful. So if you are using phi for this, you are going to have problems in this course. So this is x, I can do this, r times sine theta cosine phi, and I can do the same thing for y is r sine theta sine phi, and z is equal to r cosine theta. And the tricky part is the Laplacian del squared, and if you can write it by heart, good for you. I can't. I mean, there are ways, if you have the appetite to, I don't know, spend 5-10 minutes to figure that out. It's also good, but I didn't do it. I just copied it from the textbook. So this is,
For example, in the exam.
I will give you, yes. I don't expect, like sometimes, like for the like angular parts, I know a nice trick. I asked it once, but I told them like, this is what you are supposed to do. I don't think I'll do things like this here. I think I may, but if I do it, I will help you, right? I myself cannot write it by my heart, so I don't expect you to do it. You can just, if I forget to give you, you can ask. So this is r squared sine theta. I always write sine square here, but this time I didn't. This is sine theta, del theta, and this one is 1 over r squared sine squared theta del squared del phi squared. So suppose this is given to us, and I think some people know how to derive this. If that's your thing, you can talk to those people. So what we need to do is we need to solve minus h bar squared over 2m del squared psi plus v psi is equal to e psi. And we are going to try separable solutions. Try so this psi is going to be a function of r, theta, and phi, and I'm going to have like a radial part r, which only depends on r, and I want to have an angular part y, which is going to depend on theta and phi. So let's write this. This is minus h bar squared over 2m. So I'll copy this. So this thing, this entire thing, hitting on r and phi. Now I'm not writing the arguments of the function because I know r is a function of r and y is a function of theta and phi. So this is plus v is only a function of r, so we also need to keep that in mind, is r times y is equal to e times r times y. Now let's play with this. So this thing, let me open some space. So I know this is a r derivative, and r derivative is going to go and find something r dependent. So I'll write r here. Because y is not r dependent, it's just going to just go through, right? And also let me try to push it like this and write y here. And technically we need to switch these partial derivatives to total derivatives, right? Because there is no other variable inside r. But let me not be so pedantic. It's okay. So here theta dependent thing is going to go and find theta dependent thing. R is not theta dependent, so it's just going to move through. So this is r. And similarly here I have y, and this is r. Now I distributed r, so I deleted that. And the second step, so divide by y times r, and let's multiply with minus 2m over h bar square, so that this factor is going to go to like smaller thing here. Actually, let me also do it this way. So this is this e, I'm going to carry it to here. So this is minus e, and I'll set here 0. So let me copy and do what I just said I'm going to do. Okay, this is. So if I divide by yr, this is going to go, and I'm going to have 1 over r here. So this is going to go, and I'm going to have 1 over y here. So this is going to go, and I'm going to have 1 over y here, and this is going to go. And I also multiply with minus 2m h bar squared, so let's also do that. So this is going to be minus 2m over h bar squared, and this is also gone. And now is the part that we identify what is r dependent, what is angle dependent. So this thing, for example, plus or minus this thing only depends on r, right? Because this is r and r derivative, r squared, v is r dependent, e is a constant, right? It's just a constant. In the Schrodinger equation, we are trying to find that constant, eigenvalue. So there is no theta or phi here. And similarly, the second piece is only theta and phi dependent, right? I look at y, and y, I introduce it with theta and phi. Derivatives are theta. I think I also need to get rid of this. I need to multiply with, let me fix that, r squared. If I multiply with r squared, you can see this r squared is gone, this r squared is gone, this r squared is gone, and I need to have r squared here. Did I get that? Yes, now I fix it. Now this piece has no r, it is only angle dependent. Therefore, we should call it like, this is like a constant, like some c, and constant means it doesn't depend on theta, it doesn't depend on phi. If this is C, this thing are circled in blue is, if this is C, this is going to be minus C, right? This is like something plus something is equal to 0 equation. But typically we don't call it like this. We call this C minus L plus 1. This is also another constant. But since people have been solving these equations for like hundreds of years, literally, so they give intelligent names to constants. And we are going to find this L is going to be integer at the end. But at the moment, you don't have to assume that. Yes?
Why did we multiply it? Why did we add the r squared?
Because if I didn't multiply with r squared, there was like an r squared, and I would not be able to separate this red circled region from the blue circled region, right?
Red line, you assume it's minus L plus 1.
Yes. The red circled region is minus L plus L1. Blue circled region is going to be plus L times L plus 1.
Why did you write central potential?
Because if this is not central potential, I would not be able to separate it. Or V is here, right? V is here. Why did I? Can you ask one more time?
Isn't this just following Schrodinger's equation in 3 dimensions?
But if V, like, yeah, that's a good point. If V was a function of x, y, z, I would not be able to separate R part, right? If V is, for example, something like this, if V is a function of x, y, z, that means V is a function of R cosine theta sine phi, and there's like angle dependence inside V. If there is angle dependence inside V, I cannot separate it. For us to be able to separate it like this, V needs to be central potential. V needs to only depend on R, nothing else. That's important. Okay. If there's like separate dependence on X, Y, and Z, right, then you have angular dependence. Yes?
We take the variable minus L multiplied that one
Yes.
for the angle dependence.
Yes. Yes. So because this is a constant, right? This entire red circled region is a constant because it doesn't depend on R, right? Like there is no R dependence. And from that point of view, this is like a constant. And rather than calling it C, we call it L plus 1 because the solutions are well known and we want to connect to these well known solutions. They are indexed with L. And the other part, this blue circled region, is independent of theta and phi, and it's also constant. So we want to we are going to write the solutions in terms of special functions, and special functions have these special indices. I mean, you can also do it with C, but it's going to be a little bit roundabout. So now let's write radial equation. So radial equation is. So this, okay, blue circled region is called radial equation, red circled region is called angular equation. So let's write each 1 over r dr. Let me also switch from partial to full derivative, r squared dr times r minus 2m over h bar squared r squared v minus E is equal to, if red circled region is minus L plus 1, blue circled region is plus L plus 1.
Since we are going to find 3 different values for the solution of the Schrodinger's equation.
Yes. 3 different components, right?
So does that mean, is it related to degeneracy?
Yes, we all see the degeneracy too, right? But for the moment, you don't have to worry about this, right? We are saying here's the procedure, and this procedure is trying to separate the variables. We separate the variables, and each variable has its own differential equation. So this is radial equation. That's the name. And the second part is 1 over y, 1 over sine theta. Here I still need to keep partial derivative because y depends on theta and phi. So let me do that. Del theta sine theta del theta y plus 1 over y 1 over sine square theta del squared y del phi squared is equal to minus L plus 1. So this is the second piece. So in the remaining time I want to focus on, so this is what we call angular equation. So this is angular equation. So in the remaining part I want to focus on angular part, and in the second hour I'll spend time with radial equation. So let's think about angular equation. So let me manipulate this a little bit. So I'm going to multiply with y, erase this guy and erase this guy. And now I want to also separate this equation, right? There's like theta part and phi part. I can do exactly the same procedure. So let y of theta and phi be, so this is also a convention, like a little harder to write and ugly letters, and when I see some ugly letters in an equation it distracts me. If you also feel like me, what can we do? So it's like this uppercase theta, who knows what it is, and theta part. I mean, you could also choose A and B, but like sometimes convention matters because other people will be reading your equations easily. If you put, I don't know, K here, who knows what K is, right? But now I know theta is theta dependent. And second part is uppercase phi and phi dependent. So what I want to do is I want to substitute it here. So let's substitute. Now you can see this theta part is going to know theta part. So this is theta. And now partial derivative is going to be full derivative. And phi part is just going to walk through. And here this is only phi part. So this is phi. And this is theta is just going to go through. And this is theta. And this is phi part. So I substituted already. And I also want to multiply this with sine squared so that I don't have, so this is going to be, if I multiply with sine squared, this is one more sine. This sine squared is gone, and I'm going to have sine squared here. Good. Lastly, okay, let me do it in two steps in case you get lost. Let's divide by theta times phi. If I divide by theta times phi, I'm going to have uppercase theta here. I'm going to have uppercase phi here. And I'm going to have 1 here. And actually, let me also do it. Take this term on the other side and put it a plus. Let me put it 0, and I want to move this to the end because I want to separate each variable part from the other. Good. Now we see exactly the same thing. So there is only phi dependent part, and there is only theta dependent part. And you can call them whatever you want, but typically we call this minus m squared. And this also is going to be connected to special function indices. Then the equation, okay, this should also be, because this is no more partial anymore, like this is d, so 1 over phi d squared, d phi squared, uppercase phi, is equal to minus m squared. So I can erase this and put it here. And like we solved this so many times, the easiest thing to solve, the solutions are like a times e to the, I choose I m phi, right? Take one derivative, I m, one more derivative is minus I m times minus I m is minus m squared, so it satisfies. And the boundary condition, what is boundary condition? Psi is a function of r, theta, and phi. And when I, like in this coordinates, when I go around and come back to the same point, psi should be single valued. I should not go to some other value. If I have multi-valued function, they are bad, right? So then this means psi of r, theta, and phi plus 2 pi, but that means e to the I m phi should be equal to e to the I m phi plus 2 pi, but that means m times 2 pi should be an integer times 2 pi. That means m should be an integer. So this is the theta part. And lastly, so this, let's also get this part. So this thing is going to be equal to m squared. Let me also rearrange this. So this is going to be minus m squared is equal to 0. And I can multiply everything with uppercase theta. So this is uppercase theta and get rid of this. This is the theta equation. So this equation is not easy to solve. Like I'll just write you the solutions. The solutions. So this uppercase theta of theta are some constant times this p l m cosine theta. So the PLMs x are given by minus 1 over m, 1 minus x squared to m over 2, d dx to m PL x. So these are called associated Legendre functions. And this P with one index is so-called Legendre polynomials. And they are given by 1 over 2 to the L So these are Legendre polynomials. I don't anticipate anyone to know this, and I'm not particularly interested in special functions. But you'll see when we introduce angular momentum, there'll be a very nice way of getting these things without memorizing anything. They are going to be like this harmonic oscillator raising and lowering operators. For the moment, this is what it is, right? Yes.
Here the x's are doesn't relate to r coordinate extra.
So whenever you see x, you substitute cosine theta. right? This x is a functional variable, right? Like this is, if you want, you can put, I don't know, psi, something like that. It has nothing to do with coordinate x. So that means whenever you see x, input cosine theta. That's what it means. Maybe I can write just a couple of these and then you can see what they look like. For example, P0 of x is 1. You can use this to derive this. P1 x is going to be equal to x, and P2 x is equal to 1/2 3x squared minus 1. I just derived all of this using this so-called Rodriguez formula. I think everybody took this special functions course, right? You don't have to know this by heart, but you have seen this before and you know they have some properties. Now you know where they are useful, right? Also now let's also, so this is the P without a second index. The P with two index is like P, for example, let me write this one. P2 0 of x is something like 1/2 3x squared minus 1. P2 1 x is equal to minus 3x 1 minus x squared. Now you can see PLM is actually not a polynomial because there's square root, and this is P22x is equal to 3 1 minus x squared. So this equation also, so this one is for m bigger than 0. If m is smaller than 0, so P L minus m is written in terms of positive 1. Let me write the expression minus 1 to m, 1 minus x squared. No, not that, but L minus m factorial, L plus m factorial. This will also be coming from our nice raising and lowering operators later. For the moment, don't worry too much. So this is PLM. Whenever you have negative, you take the positive one and use this formula. Then, okay, let me write this full solution and finish it there. The full angular part is y, L, m, theta, and phi is equal to 2L plus 1 over 4 pi L minus m factorial, L plus m factorial. So this is inside e to the I m phi p L m cosine theta, and the normalization is d. Okay, let me write. So this d omega is defined. This solid angle is defined as sine theta d theta d phi, and the orthonormality is something like that. D omega, take one of them, y L m theta and phi. Take one more and take one of them complex conjugate. Put m prime and l prime. They're orthonormal. Delta L, L prime, delta M, M prime. That's why you have these weird factors, so that this thing can be nice. And if this thing is nice, right, all these expansion theorems, we can just work them through without worrying about these factors. And lastly, normalization. So this, the omega y squared is 1. And also we separately normalize, that's also the convenient convention. We also, the r squared r is also 1. Important part is like there is this r squared term in the volume integral. Good. So this is the angular part. In the second r, I'll think about radial part.